Well, now let's study fluids in motion, having looked at static or non-moving fluids. We'll begin our study of fluid dynamics with the first principle known as the continuity equation. If we have a continuous flow of water through a hose, then it must be that we've got the same amount of fluid passing per second any 2 points. So if we consider, say, a point here and a point here, even though the cross-sectional area of the hose is different, you must have the same amount of fluid per second. So the number of liters or kilograms of water per second must be the same at any point. Now, the amount of fluid per second we're going to define as the rate of flow. So we'll have the same rate of flow here and here. So first, let's get a relationship for rate of flow. Consider a uniform cross-sectional area A and a fluid element. Now that fluid element has length L. If the fluid's moving at speed V, and if this is the fluid that's going to go by in time t seconds, a distance is a velocity times a time. So that's the length of that fluid element. A volume is a base area times a height. And the base area in this case is the cross-sectional area A, and the height or the length is the speed vt. Now we have to be a little bit careful here because we have velocity and volume, both of which can be represented by v, so that's why I wrote it out as vol. We define the volume rate of flow as being the ratio of the volume flowing by in a given unit amount of time. Using our expression here, cross-sectional area times speed times time, divided by time, we see that the volume rate of flow is the product of cross-sectional area and fluid speed. So we'll introduce a symbol R for rate and V for volume. So this is volume rate of flow. That's the ratio of volume to time, and it's the cross-sectional area times the speed. So I'm going to write this out as vol. Now, sometimes, instead of giving the volume rate of flow in cubic meters per second, we'll give the mass rate of flow in kilograms per second. So a mass rate of flow is a mass of flowing fluid per unit time. But we know that density is mass over volume, so that mass is the product of density and volume. So the amount of fluid mass that passes by is the density of the fluid times the volume that flowed by. And of course, the ratio of volume to time we just defined above as the volume rate of flow. So the mass rate of flow and the volume rate of flow are related to each other. Now, the continuity equation that we stated earlier simply said, or the continuity principle that we stated earlier, simply said that at any 2 points along a continuous flow, the volume rate of flow has to be the same. So if we call those 2 points 1 and 2, it must be that the volume rate of flow, which we just defined as the ratio of volume to time, let me clean that up a bit. So it's the ratio of volume to time. That's got to be the same at any 2 points. So if we call the 2 points 1 and 2, product of cross-sectional area and speed, which is the volume rate of flow, must be the same at those 2 points. That is the principle of continuity. And we'll just make this a little summary. The mass rate of flow is the density times the volume rate of flow. Then we can put a box around it. And that defines or encapsulates the definitions that we have so far, volume rate of flow, and also the continuity principle, which states that those 2 rates of flow must be the same. Now, this is introductory physics for life science, and some typical flow rates. Urine will flow out of your body at about 10 milliliters per second, unless your ureter is blocked. More talk about the prostate later. Blood flow is about 5 liters per minute. All of your blood in your body, about 5 liters, flows through the heart and lungs every minute to be oxygenated. The flow rate of your lungs, your tidal volume, the amount that goes in and out, is about 500 milliliters, and a typical period for the respiration cycle is about 5 seconds. If you're really exercising hard, you might sweat at 4 liters per hour. Typically, this would be a lot less. And a big tree will suck up about 10 liters per hour of water under hot sun. So a flow rate is a volume over time. And volume units can be liters, cubic meters, or milliliters. The standard unit, of course, is cubic meters. And time units can be hours or seconds or years. So any ratio of volume to time is a volume rate of flow. Let's do a simple example. So this garden hose fills a 10-liter pail in 20 seconds. So 10 liters is a volume. The time is 20 seconds. And we want to find the speed of the water here inside the hose. That's V hose. And then here as it exits the nozzle. That's V nozzle. Now, clearly there's a difference in radius there, so that's going to lead to a change in speed. Now, the SI unit of volume isn't the liter, it's the cubic meter, and a cubic meter is 1,000 liters. So that's 0.01 liters, and I ran out of room there, so I'll put it up here. 0.01 cubic meters, rather. Okay, so we'll set up our continuity principle. Volume rate of flow is volume over time is going to be the same in the hose as it is at the nozzle, because if those two flow rates weren't the same, then in between fluid has to be appearing or disappearing, and that's clearly not possible. So what is the volume rate of flow? Well, we know it's about 10 liters over 20 seconds, or 0.01 cubic meters over 20 seconds. And the cross-sectional area of this hose is going to be circular. So A equals a circular cross-section. And the area of a circular cross-section is pi r squared. And the radius here is 1 centimeter, or 0.01 meters. And the area at the nozzle is given as 0.2 centimeters, so that will be 0.002 meters squared, V nos. So there's two equations. Here, you can solve this first statement for the speed in the hose, and it works out to about 1.5 meters per second, I think. And then you can solve this equation for the speed at the nozzle, and it works out to about 40 meters per second. It's a lot faster. And the reason why, well, is ultimately related to the continuity principle. The area got a lot smaller, so the speed had to get a lot greater in order for the flow rate to be the same through that nozzle. So that's the first principle of fluid dynamics, the continuity principle. It says fluid cannot be created or destroyed between any 2 points along a contained flow. The second principle of fluid dynamics is known as Bernoulli's theorem. And Bernoulli's law, Bernoulli's theorem, talks about the pressure that the fluid experiences at various points along the flow. And that pressure will change. So it turns out that what Bernoulli's law says is that there's a trade-off between pressure and height, or between pressure and speed. There's a three-way trade-off there. Now, in classical mechanics, a throw and ball, you know there's a trade-off between speed and height. So if you throw it fast, as it gains height, it's going to lose speed. Well, for a contained fluid, it's a three-way trade-off. So right here, the fluid's moving at a certain speed. If the dimensions of the pipe don't change, then the speed will be the same at the top because the cross-sectional area is the same. That's just the continuity principle, which says same area, therefore same speed. But clearly here, we've gained height. And so we gained height, but we didn't lose speed. Well, what did we lose? We lost pressure. The pressure will be a lot higher at the bottom than it is at the top. So this was a trade-off between pressure and height. We can also have a trade-off between pressure and speed. We'll see here that the fluid's going to be moving relatively slowly because the area is large. Over here, where the area gets really small, the speed is going to get really large to compensate. So how is it that we got that tremendous gain in speed? Well, it turns out we had a drop in pressure. We went from a very high pressure reading to a very low pressure reading. And if you put pressure gauges on there, that will be confirmed. That's an experimental result. So Bernoulli's law is all about this three-way trade-off between pressure, height, and speed. It's different from classical mechanics because classical mechanics just had a trade-off between speed and height. Let's derive Bernoulli's principle. It comes from the work-energy theorem, which says mechanical energy changes when there's non-conservative forces. By mechanical energy, we mean the sum of kinetic and potential. And by non-conservative forces, we mean forces that change mechanical energy, such as applied forces and friction. Well, we have applied forces. They're the ones coming from the pump that create pressure variation in the fluid. So here we have a different pressure on two sides of this little fluid element. Again, it's a tube of cross-sectional area A. And we want to come up with an expression for work. Well, from basic mechanics, we know that a work is a force times a displacement. From our pressure definition, we can cross-multiply and solve for force. It'll be a pressure times an area times a displacement. But of course, there were pressures on both sides, and work is going to be done if those two pressures are different from each other. So it's really a net pressure that does work. If the two pressures are the same, then there is no net force, and therefore no work done in total. All right, and what we notice, though, this is initial pressure minus final pressure. Right? The initial was acting on this side, the final was acting on that side. What we notice is we have an expression here at the end that says cross-sectional area of the hose times the distance d. Well, that's a volume. It's the volume of that little fluid element of interest. So that's the amount of work that's done, non-conservative work, by the external forces that are pushing on the fluid and moving that little element along. Now, if there's no change in pressure, then there's no work done. And we go back to our statement of mechanical energy conservation. If the pressure is constant, then that's just zero, and we just have a trade-off between potential and kinetic energy. So when the fluid's exposed to the air, as it falls, it picks up speed exactly like we would expect it to do according to the principles of classical mechanics. And I'll just do a big letter V to indicate that it's going faster there. So that's if the pressure doesn't change. Well, what if the pressure does? Well, then let's substitute that work term back into our derivation. So this was the initial mechanical energy, and I've substituted in half mv squared for kinetic and mgh for potential energy. This is the non-conservative work. This is the final kinetic and potential energies. And now I'm going to do something that initially doesn't seem like it's going to help. I'm just going to divide through by volume. Because if I'm going to divide the equation, I have to divide everything. This really was a volume, right? Because, I'm sorry, if we go back here, I should write volume here. I'm going to give you seasickness with all these bouncing around, I know. All right, now that simplifies that term quite a bit, right? Because now suddenly, boom, that volume is gone. But it looks like we've made all the other terms worse until we realize that the ratio of mass to volume, that's a density. And so we really have made a step forward. So we can say 1/2 mass over volume will be rho v squared plus mass over volume will be rho gh. So the initial value of that. And so that's really an energy per unit volume. So that's in units of joules per cubic meter. And then that was the pressure difference. And then on this side, it'll be 1/2 rho v squared plus rho gh final. And you remember my sort of calligraphy comment that you had to make your rho's look different from your p's. Well, the derivation of Bernoulli's theorem is complete if we take this final pressure term and throw it over here, because then all three quantities on this side relate to the final location, and all three on this side relate to the initial location. And Bernoulli's theorem is therefore displayed this way. It says 1/2 rho v squared plus rho gh plus p at one point I along the contained flow equals 1/2 rho v squared plus rho gh plus p at a different point. So this quantity is a constant. Now, what is that quantity? Well, it's related to energy, right? This is the mechanical energy per unit volume. But then this pressure term is sort of like a work term. So this is a rearranged conservation of energy statement, okay? It doesn't say that mechanical energy is conserved because there's actually non-conservative work done. It says that this quantity is conserved. And again, it tells us that there's a trade-off between height, speed, and pressure because we see them all together on one side. So that if, say, the speed were to be really large, or rather if the speed were to get large and increase, then either the height or pressure would need to decrease. So there is a trade-off there between those three quantities. And we'll look at some demonstrations and discuss that in more detail in our class time together. Let's just practice on a simple exercise. A key point here is that when a fluid is exposed to the air, it's at atmospheric pressure. So the first question that everyone does with Bernoulli is the leaky tank. And because it's an open tank, it's atmospheric pressure at the top. Because the air is squirting out of the hole, it's exposed to the air, that's also atmospheric pressure. So we're going to apply the continuity principle, and we're going to consider a little element of fluid up here at the top and a little element going out the hole. Well, we see that in terms of the flow here, it's kind of deformed, but there's a really large cross-sectional area here, because it's a huge tank, and a relatively small cross-sectional area here. So it's going to be A times V at the top equals A times V at the hole. And the top is pi times 2 meters squared times the speed at the top. That will equal pi times 0.05 meters squared at, okay, sorry about that. And now this will be the speed at the hole. Now, the pi is going to cancel, but we notice here that the speed at the top is an unknown, and so is the speed at the hole. So we would typically have two unknowns in this equation now, and it wouldn't be solvable. But in this case, we're going to make an approximation. Because this is 5 parts in 100, divide by 2, it's 5 parts in 200. So that's 1 part in 40, and then you square it. It's 1 part in 1600. So we're going to make the approximation in this case, and it only works where you've got a really big area and then a really small area. We're going to say that the fluid flow rate on the really big, the fluid flow speed on the really big area is about 0. We're going to take it to be 0. That only works when you've got a big difference in areas. And if you think about it, this is kind of like a bathtub. When you pull the plug on a bathtub, the water goes really quickly down the drain, but the level in the tub moves a lot more slowly. Now this is just going to make our lives easier, because when we set up the Bernoulli, we're going to say a half rho v squared plus rho gh plus pressure at the top is going to equal a half rho v squared plus rho gh plus pressure at the hole. That's how we set up Bernoulli. So what do we know? Well, we just said up at the top, this is going to be 0. The height up at the top, we can see, is 3 meters. The pressure up at the top is atmospheric. At the hole, the speed is the unknown, the height is 0, and the pressure is again atmospheric. All right, so not having that term means this one is just wiped out. And rho is just going to be the density of water. It's 1,000. So we could say 1,000, and we won't bother with the units, times g times 3, plus atmospheric pressure. This is the unknown. This is going to be 1,000 over 2 v squared plus atmospheric pressure. Putting in the density of water is 1,000, and putting in the height is 0 there. So that whole term disappeared, and then again it was atmospheric pressure both at the top and at the hole. So it actually cancels out, and well, so does the density too. You could cancel out the 1,000, and you could just cross multiply up the 2, take the square root, and solve. It ends up being, I think, about 7.7 meters per second. And that's the first classic Bernoulli problem. So now we know how fast the fluid's coming out of the hole. We wrote a continuity statement and a Bernoulli statement. Let's try another problem. And this one I'm going to ask you to just simply write a continuity statement and write a Bernoulli statement. Now, having watched me do one, I'm going to ask you to try doing this one yourself. Okay, so try substituting in here area times speed in the hose is area times speed in the nozzle. So that would be a continuity statement, and then a Bernoulli statement. And don't solve for anything, just write them and maybe substitute in what we know or make a list of what we know on the side, whichever you'd rather. And pause the video for a second, and then try doing that on your own, and then turn the video back on and see how you did. Okay, so hopefully you took a crack at this and you saw that I was missing something here that's important, volume rate of flow. Because in the hose, we know it's 3 centimeters, so that would be pi times 0.03 squared times the speed in the hose. And then at the nozzle, it's going to be pi times 0.01 meters all squared times the speed at the nozzle. And this area ratio is only 3 to 1. It's not as large as the previous question, so we're not going to be able to assume that the hose speed is 0. But we do have the volume rate of flow, because you see here you have volume over time. This is a volume rate of flow. Now we have to convert units, because 0.75 liters, a cubic meter is 1,000 liters. And so this works to be 7.5 times 10 to the power negative 4 cubic meters per second. So that's our volume rate of flow, and we could put that right here. And I'm going to have to write very carefully. And I'm not going to be able to fit the units in, I don't think. Yeah, this would be meters cubed per second. Squeeze it in there. So now that statement could be solved for those two speeds, okay? And again, the area ratio wasn't as large in the previous question, so we can't assume that this one is 0. Next, we'll write a Bernoulli statement. So that quantity, half rho v squared plus rho gh plus pressure inside the hose, will equal the value of the quantity, half rho v squared plus rho gh plus pressure, as it emerges from the nozzle. So let's think. When it emerges from the nozzle, it's at atmospheric pressure. When it emerges from the nozzle, it's at a height of 2.5 meters. When it emerges from the nozzle, its speed is an unknown v nos that we could get by solving this equation, but we didn't do that. The pressure in the hose in this equation is the unknown, the height is 0, and the speed is the speed in the hose, which again could come from continuity, but we didn't bother solving that. Now we are dealing here with water. We'll assume it's water, and so this is going to be 1,000 over 2 times v hose squared. We'll just assume that we've solved for that, plus the pressure equals 1,000 over 2 v nos squared plus 1,000 times g times 2.5 plus atmospheric pressure. And so these equations would solve really well. You solve the continuity statement for the two speeds, plunk them in there, and solve this equation for the unknown pressure, which is what you were asked to find. All right? So that's how we work with the two principles of fluid dynamics, the principle of continuity and Bernoulli's theorem. And we'll take these topics up in more detail when we meet together in class.